Welcome to The Explainer. Today we're going to completely demystify the foundational language of computers. Have you ever wondered what's actually happening under the hood of your smartphone or laptop? Well, we're going to break down how to translate human numbers into machine code. Consider this your ultimate guide to decimal to binary conversion explained simply and visually. We've got a fantastic visual journey queued up for you, so let's get right into it.
So take the number 205. To you and me, that makes perfect sense, right? But to a computer, it's total gibberish. How do you actually say that number in the only language computers actually understand? Well, before we start throwing a bunch of math at you, we first need to figure out exactly why computers require a completely different number system in the first place.
Here's our roadmap for today. We'll look at why computers use binary, compare decimal and binary systems, cover the divide by 2 method, learn the powers of 2-trig, and wrap up with advanced negatives and giant numbers.
All right, Section 1, why computers actually use binary looking under the hood.
Think about the physical circuitry inside your devices. First, you have analog signals, which involve infinite states and messy, varying voltage levels. Trying to control that reliably at lightning speeds, it's a nightmare. Instead, computers rely on electronic circuits that use discrete values. It is vastly easier and way more reliable. We just use 5 volts for on, which represents the digit 1, and 0 volts for off, which is our 0. There's literally no in between. It's just on or off.
And what's really fascinating here is how perfectly that physical hardware maps onto Boolean logic. This is a mathematical concept pioneered by George Boole way back in 1847. The electronic circuits essentially act as logic gates. They either allow signals to pass through for a true state or stop them for a false state. And boom, those true and false states map flawlessly right onto our ones and zeros.
Moving on to Section 2, Decimal versus Binary Systems, the what.
If you're looking to understand the binary number system for beginners, this comparison is the perfect starting point. To get decimal and binary explained simply, think about what we natively use. We use the base 10 decimal system, which gives us 10 distinct digits to play with, from 0 all the way to 9. We have 10 fingers, so base 10 makes total sense to us. But computers, as we just saw, they use the base 2 binary system, meaning they only get 2 distinct digits, 0 and 1. At the end of the day, computer number system conversions are really just about translating between our base 10 and their base 2.
To really grasp this, think about how counting actually works. In decimal, when you're counting up and you hit 9, you literally run out of digits. So what do? You reset that column to 0, and you bump the next column to the left by 1, which gives you 10. Binary does the exact same thing, but you run out of digits much, much faster. You reset immediately after the number 1. So counting goes 0, 1, and then you're out. You carry over, making the next number 10, then 11, then carry over again to 100. It's the exact same logic, just with a whole lot less room to maneuver.
All right, Section 3, the divide by 2 method, the standard algorithm.
If you want to know how to convert decimal to binary step by step, this repeated division by 2 method is your gold standard. To convert any decimal to binary, you just repeatedly divide your target number by 2. You keep track of the remainders along the way, which, logically, will always be either a 0 or a 1. You take the new quotient, divide it by 2 again, and repeat. Now, the absolute most crucial part, when you finally hit a 0 quotient, you stop, and you have to read your list of remainders completely backwards, from bottom to top.
Here is how that brilliantly plays out on paper. Look at the number 19. We divide 19 by 2, which gives us 9 with a remainder of 1. Then we divide 9 by 2, getting 4 with a remainder of 1. We just keep going until we hit 0. Now notice that giant arrow? That is explicitly showing you how critical it is to read those remainders from the bottom up. When we read upwards, we get 1, 0, 0, 1, 1.
Okay, time for some hands-on decimal to binary conversion examples. I want you to pause this explainer right here, grab a scratch pad, and see if you can repeatedly divide the number 205 by 2 to find the binary sequence. Go ahead, give it a shot.
All right, did you get it? If you remembered to read your remainders right to left or bottom to top, and you ended up with 1, 1, 0, 0, 1, 1, 0, 1, you absolutely nailed it. You just successfully spoke to a computer.
Let's move to Section 4, the powers of 2-trig, a great student shortcut.
Honestly, this is one of the best binary conversion tricks for students. Instead of doing all that dividing, we're going to use place values. In decimal, our columns are the ones, tens, hundreds, right? But binary place values are simply the powers of 2, increasing from right to left. Try to lock this sequence into your brain.
1, 2, 4, 8, 16, 32, 64, and 128. Every single column is just double the one before it.
To use this trick, you just find the largest power of 2 from that sequence that fits into your target decimal number. If it fits, you write down a 1 for that column, and you subtract that value from your total. Then you literally just move down the line to the right, checking if the next power of 2 fits into your leftover amount. If it doesn't fit, just write a 0 and move on.
Let's look at this whiteboard example. We want to convert the number 186. Looking at our powers of 2, does 128 fit into 186? Yes, it sure does. So we write a 1 in that column and subtract 128 from 186, which leaves us with 58. Next column down is 64. Does 64 fit into 58? Nope, it's too big, so we write a 0. The next column is 32. Does 32 fit into 58? Yes, so we write a 1, subtract 32, and just cascade that logic all the way down to 1. It basically turns into a simple game of mental subtraction.
Finally, Section 5. Advanced Binary, handling negatives and giant numbers. So what happens when we step outside of basic positive numbers? Since computers don't have a dedicated minus sign built into their physical hardware, they use a brilliantly clever trick called 2's complement. To make a number negative, you take its binary sequence, you flip all the bits, so every 1 becomes a 0 and every 0 becomes a 1, and then you simply add 1 to the result. For example, the number 6 is 0110. Flip the bits to 1001, add 1, and you get 1010. And boom, that exactly represents -6. It's such an elegant mathematical workaround.
Now, what about giant numbers? Imagine trying to repeatedly divide this massive decimal number over 2 billion by 2, by hand, using our standard algorithm. It would take an entire notebook of long division, and frankly, human error would be almost guaranteed at some point.
The amazing mathematical shortcut here, and programmers use this all the time, is to divide by 16 instead of 2. Doing this translates the decimal into a base 16 hexadecimal equivalent. Why do we care? Because base 16 hex values can be instantly and flawlessly converted into binary using a really simple standard lookup cable. It saves an incredible amount of time and division steps.
So the crucial takeaway from this entire explainer is that binary isn't some incomprehensible magic. It is literally just a different way of counting, entirely dictated by the physical realities of electronic circuits. And to prove that you've really got this down, I have a challenge for you. See if you can convert your own age into ones and zeros using that powers of 2 trick we just learned. Think about it. If the entire modern digital world is built on math this simple, what else could you decode if you just took the time to look under the hood?